Okay, I'm sure that we'll get a few more folks logging on, but we'll start. Good afternoon and welcome to the Spring CESU, that is Cooperative Ecosystem Studies Unit, webinar series. My name is Lisa Gerloff and I am the Executive Director of the Rocky Mountains CESU. Okay, I'm sure that we'll get a few more folks logging on, but we'll start. Good afternoon and welcome to the Spring CESU, that is Cooperative Ecosystem Studies Unit, webinar series. My name is Lisa Gerloff and I am the Executive Director of the Rocky Mountains CESU. This year with our series, we are joined by the Colorado Plateau and the Desert Southwest. Each of our CESUs has selected a project and a researcher to showcase the diverse range of good science that is accomplished through our regional networks and the impacts it has on management decisions. The Rocky Mountains kicked off the series with the presentation by Haley Johnson a couple weeks ago. Haley's a recent University of Montana graduate, drawing on research from Yellowstone and Stephen Mather Wilderness and other public lands in the West. Haley explored how social science can help manage growing recreation demands on public lands. In a month, we'll have, on April 23rd, the Desert Southwest will be represented by Mallory Davies from the University of Arizona School of Natural Resources and the Environment. Mallory's webinar is titled Linking Diet, Migration, and PD Invasion Risk, a decade of long-nosed bat research in the Desert Southwest. In just a few minutes, I'll put a link to my webinar page in the chat. From there, you'll be able to register for Mallory's webinar on April 23rd and find a link to the recording of Haley's presentation. Today is Colorado CESU's Day, and I'm happy to have Dr. Temulin Sankey with us. Dr. Sankey teaches remote sensing and directs the Remote Sensing and Geoinformatics Research Lab at Northern Arizona University in Flagstaff. Her research focuses on satellite and UAV remote sensing applications in environmental science and ecological studies in forests, woodlands, and rangelands. Dr. Sankey will speak for about 30-35 minutes, so we'll have plenty of time for questions at the end. I'll remind you, but please put your questions in the chat box. With that, I welcome Dr. Sankey and turn it over to her.
All right, great. Thanks, Lisa. Are you hearing me okay?
Yes, I can hear you great.
Okay, great. Well, thanks for that introduction, Lisa. I am a professor at NAU. I've been here at NAU since about 2013. As Lisa mentioned, I run the Remote Sensing and Geoinformatics Lab here at NAU. I was trained as a remote sensing scientist, plant landscape ecologist at Montana State University, where I got my master's and my PhD. And since then, I have used all different types of remote sensing data, specifically multispectral, hyperspectral, and LiDAR data to study different kinds of ecological and environmental topics. From a technical remote sensing perspective, I am particularly interested in data fusion, in particular combining optical data with LiDAR data. And so I'll be talking a little bit about that today. I have a fairly big research lab group here. Currently, we have 2 postdocs, 1 research staff, 5 PhD students, and 1 master's student in my lab today who are doing all different types of remote sensing projects. But today, Among them, I will be presenting work that's being done by a PhD student of mine, Jonathan Tenney. Jonathan is a fourth-year PhD student in the ecoinformatics program, funded by a USGS grant and through the CESU agreement. And his work is largely focused on fuels monitoring and measurements, and then fire behavior modeling associated with those data sets. And so before I get started, I also just wanted to say that the work that I'm presenting today is Jonathan's dissertation chapter number 1, which has already been published in the International Journal of Wildfire. I just put the paper up here. If you have detailed questions, you can look up the paper afterwards. So just really briefly as a background, forest dynamics in the Western USA have changed a lot over the last century or so, or a little bit more than that. More specifically, both tree density and canopy cover have increased a lot, largely due to the fire suppression policy we implemented throughout the last century or so, as well as grazing and other variables like that. As a result of that, wildfires are increasing in the USA a lot. And so today we see on an annual scale, total burned area is increasing. As a result of that, the costs associated with fighting these fires have increased a lot, as most people here in the room, I'm sure know. Currently, it's estimated that we're spending roughly about $100 billion a year to fight these wildfires, some of which are burning at catastrophic risks. And so the federal government is taking lots of initiatives in starting to implement large fuels reduction treatments across the West. The Forest Service, for example, is planning to implement fuel treatments over 50 million acres over the decade, specifically focused on high burn severity or high fire risk areas. Arizona has been part of this kind of an effort for a while now, specifically through an initiative known as 4FRI, which stands for Forest Restoration Initiative. 4FRI was one of the first and the largest forest restoration initiative or effort, specifically with a goal to reduce catastrophic fire risks. Through this initiative, the Forest Service and the state of Arizona set out about a decade ago to treat roughly about 2 million acres across 4 national forests that we have in Arizona. And so here in the green polygon across Arizona, I showed the 4FRI area where treatments are happening. And more specifically, across this area, we have been implementing both mechanical thinning and prescribed burning treatments to reduce fuel. And so this initiative started about a decade ago, and so my research lab group has been monitoring this initiative and the impact of this initiative, largely using space-borne multispectral satellite data like Sentinel and Landsat, as well as using more recent thermal and hyperspectral images like EcoStress and EMIT. And of course, we're also using Lidar data to monitor these treatments and what the impacts have been. We're doing this because, of course, there is a huge demand for decision support tools to plan and facilitate these really large scale or regional fuel reduction treatment efforts. Of course, at the core of these kinds of decision support tools is a vegetation structure data. Everybody needs locally specific, detailed vegetation structure data to make informed decisions for these treatments. And so a lot of our work have focused on providing these kinds of detailed vegetation structure data. Our research goals consistently have been to estimate vegetation structure, to evaluate current fuel structure. And also we have been trying to monitor changes in the vegetation structure that result from these treatments. And then in some studies, we often compare the post-treatment vegetation structure against desired conditions or the prescription goals to see if the prescription goals have been met or not. So before I go into the details of the remote sensing-based analysis, I just wanted to quickly review how fuels are typically monitored using conventional approaches. As most of us know, of course, we normally do this out in the field. We go out in the field and then we measure tree diameter at breast height. Of course, in the field, we measure tree height and canopy height and height to the base of the crown, things like that, all in the hopes of estimating total foliage biomass inside the field plots, from which ultimately then we hope to derive this kind of a vertical profile of canopy bulk density. In other words, the vertical distribution of foliage biomass inside these plots. And so this kind of a measure ultimately is our kind of end goal for a lot of these monitoring efforts. And field-based measurements, of course, are highly accurate and really desirable data set. But of course, it comes with two major challenges. One is that they're very, very time-consuming, labor-intensive. As a result of that, they have very limited spatial coverage. Typically, we have a few plots covering a large area as representatives. Another problem in Arizona is that woodlands and shrublands and chaparral type of vegetation are fairly common across Arizona, and many of these field-based fuel monitoring approaches are difficult to apply in those types of ecosystem types. And so, of course, one obvious thing that comes to our mind is, well, we should use some kind of remote sensing data. In particular, I'm sure many of you have thought about using LiDAR data instead of or in addition to the conventional field-based measurements. So here I'm showing just a view of a airborne LiDAR data set as an example. I'm going to play this one more time. More specifically, this is a LiDAR data set, airborne LiDAR data set from a UAV platform. And this is a typical or a more common LiDAR data set where we have a single return. And so what that means is that the LiDAR pulse doesn't penetrate through the top of the vegetation canopy. And so from this data, although you can estimate tree height and canopy diameter, things like that, as you can see, we don't see the vegetation below those canopies. Also, more importantly, you do not see the trunks of those trees, and so you can't measure basal area, things like that that are important in measuring fuel structure. And so we have been using terrestrial LiDAR data instead of airborne LiDAR data because of these challenges, because we think that terrestrial LiDAR data can provide faster and more precise measurements compared to the labor-intensive field-based measurements, but can also ultimately provide kind of a similar kind of a vertical profile of fuel structure that we're after. More specifically in this project, we are using a terrestrial laser scanner, or TLS, known as BLK360, which is a very small, compact, and more affordable LiDAR sensor. And so we wanted to test this sensor in this study. Before I talk too much about the terrestrial LiDAR data itself, just quickly, I wanted to summarize what the data tells you, what it looks like. Of course, you put the terrestrial LiDAR on a tripod like this, and then the scanner is shooting out laser pulses. And when each pulse hits a in-Earth surface object, it bounces the signal back to the sensor. And so at each one of these points where the laser pulse hits something, of course, we get three different measurements, the X and the Y coordinate, as well as the Z coordinate. And the Z coordinate is simply just the vertical measurement or a coordinate. Using the Z coordinate or the Z dimension, we estimate things like ground height, ground elevation, or vegetation canopy height, or a building height, things like that. And then, of course, the LiDAR point cloud data can be rasterized, like I'm showing here in panels B and C, to derive other data products. Similar to an airborne LiDAR data set, of course, terrestrial LiDAR data can be used to segment or delineate individual tree canopies and then make very similar subsequent measurements to derive various individual tree characterization metrics. One key advantage, though, of terrestrial LiDAR scanner is that it gives us a very, 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 very high resolution data. You can have thousands of LiDAR returns or points per square meter, using which you can study processes that are, that operate at millimeter or centimeter resolution. And so that is a very useful aspect of the data. However, a terrestrial LiDAR data set does have one important or two important limitations. One is a fairly limited spatial coverage or spatial extent, which is determined by how far each laser pulse can travel. This is known as laser range. And so here I show data sets that you can get from two different terrestrial LiDAR scanners. If you had a laser range that had a, several hundred meter or up to a kilometer range, then you could put down your terrestrial LiDAR scanner at a yellow spot like this, and then you'd be imaging a circular area 360 degrees around you, covering this kind of an area. Whereas if you had a smaller range, you'd cover a much smaller radius, like I show here on the right-hand side. Another complicated thing about terrestrial LiDAR data is that if your laser scanner was sitting here and sent out laser pulses, it hits this first tree and bounces back to the sensor. What that means is that it doesn't then penetrate through that tree and keep on going. Instead, that tree blocks everything behind it. So behind that tree, you'd have a huge hole in your data and a big gap. Therefore, we typically put our terrestrial LiDAR scanner at several different places, so you can view your target object from multiple angles, and then you can stitch those data sets together to come up with a one complete mosaic in the center of the total area imaged, where you have a full data set with no gaps. And so when we can't see behind an object like a tree, that is called an occlusion. In our project, we were evaluating two important aspects or questions. One was if we wanted to quickly and efficiently evaluate and characterize fuel structure in the field, should we have multiple scans, which is a time-consuming process afterwards because you have to carefully stitch together and these different scans and pre-process your data, or should we have a single scan to quickly measure fuel structure? If so, what about occlusion? How are we going to deal with occlusion? And so these are the types of questions we were addressing in this research project, in addition to being able to estimate fuel structure. So this project, we implemented it in southeastern Arizona. Here on the far right-hand side, I show a map of Arizona. The study area is near Phoenix and Globe, Arizona, more specifically, covering roughly about 14,000 acres in the Tonto National Forest. There, across an elevation gradient, we were studying 3 different vegetation communities or vegetation types. One is a ponderosa pine mixed with oak as an understory. Secondly, pinyon juniper mixed with oak also. And then thirdly, a chaparral vegetation cover type, which is dominated by manzanita and oak mix. And so across these 3 different vegetation cover types, we had 68 plots in which we were making 2 different types of measurements. One, of course, all of the conventional field plot-based measurements that we normally traditionally make. And so we made all of those measurements inside our plots. In addition, we put a LiDAR scanner in the center of our circular plot that had 11-meter radius. In addition, we had 3 other locations from the perimeter of the plot looking in with the LiDAR scanner to get us 4 different scans. And so we could compare a single scan from the center versus multiple scans from 4 different angles to measure all these different kinds of variables. Lastly, we also had 4 different quadrats inside these plots to measure surface fuel, in other words, understory herbaceous vegetation, things like that were measured inside these quadrats. So, of course, from the LiDAR data, what we're really after is the vertical profile of the vegetation structure. More specifically, the first metric you can derive is a leaf area density along a vertical profile. And so how do we get that? What do I mean by that? If we were to divide each plot, the vertical space and the horizontal space, into many of these little tiny cubic areas, also known as voxels. Within each cubic area, we can track each laser pulse to see if it hit a vegetation surface, like a leaf area, or if it went through an empty space and traveled to the next voxel, or if it hit a bare ground surface, things like that. And so if we were to count every single laser pulse that traveled through every single voxel inside our plot, we can then sum up those measurements and ultimately calculate the ratio of leaf surface area or vegetation returns that we hit, as well as occlusion, as well as empty spaces we hit. So then ultimately we arrive at a map like this, where I show you like the traces of every single laser pulse. The blue pulses, of course, are laser pulses that hit an empty space and kept on traveling outside of our plot. And then the green and the light green pulses are laser returns that hit vegetation. And then the brown, of course, is bare ground or ground surface that we hit with the laser pulse. And so we can classify each pulse into a foliage, non-foliage, or occluded, or an empty spot. Here in the bottom panel, I show what I mean by an occlusion. So if you had a laser scanner here and you had a big canopy right above it, then of course you can't see what's behind it. And so you see like a big hole in your data. And that's what I mean by occlusion. So if you were to aggregate all of your measurements from your individual voxels, ultimately then you come up with a vertical profile like this. Of course, on the y-axis, we have height above ground in meters, and then on the x-axis, we have leaf area density, or LAD. It's just measuring the leaf surface area and the density of that surface area that we were hitting. And the way you interpret these vertical profiles, of course, is that here, for example, at about 5 meters above ground, we see maximum amount of vegetation biomass or vegetation density. Then we see a little bit of a gap at about 9 meters, and then above 10 meters, we see a whole bunch of vegetation leaf area up there, indicating a second canopy layer, for example. So here in this plot, we are seeing 2 different vegetation canopy layers at different heights. Our end game, of course, is to convert our leaf area density to a biomass measurement, like a fuel biomass measurement, or canopy bulk density profile. And so ultimately, we want to convert our vertical profile of leaf area density to profiles like this on the right-hand column that I'm showing. That is like a vertical profile with height on the y-axis, but canopy bulk density measured in kilograms per meter cubed area. And so these kinds of vertical profiles are endgame in this project. And so up on the top panel, I show the LiDAR data set from a chaparral plot where we see a strong, consistent trend between conventional estimates versus a LiDAR-derived biomass measure or canopy bulk density measurement. In the second row, I show PJ Oak LiDAR data and the vertical profile, where we see some separation between the 2 measurements at varying heights. And then in the bottom panel, I show a ponderosa pine oak plot, where we, of course, see those 2 canopy layers, but also the 2 data sets have slightly different estimates at that plot. And so how do we get there? Of course, we start out with our leaf area density measurements, and then we're using leaf mass per area measurements to arrive at canopy bulk density. These leaf area or these leaf mass per area measurements are coming from previous studies in the literature. So we looked up the leaf mass per area for our dominant species, and then we're using them as regression coefficients to arrive at fuel canopy bulk density measurements. And the key advantage, of course, of this approach is that you don't have to cut down and clip and weigh all of the vegetation biomass in the field. You could make your LiDAR measurements and then apply coefficients from the literature. And so ultimately, I just wanted to show you 2 important things. This kind of a vertical profile derived from the LiDAR data of canopy bulk density shows that below 1 meter, for example, here in the right-hand side, there is a fair amount of surface vegetation biomass down here. And then we have fuel strata gap to about 8 meters or so. But then in this vegetation community type, at about 20 meters above ground, we have a lot of fuel. And so that's kind of how we interpret this profile. And this, where this maximum bulk density is occurring is one of the key measurements we're making from these profiles. And when we compare the lidar-derived estimates to the conventional estimates from our plots, we see pretty strong agreement between those two measurements that are statistically significant, although we see a weaker correlation with the maximum canopy bulk density measurements. In terms of surface fuel metrics below 1 meter, we see still significant but lower correlation. This is because this relationship seemed to vary a lot depending on the vegetation cover type. And most surprisingly, what we found in this research is that you can estimate fuel structure just as efficiently from a single scan as opposed to a multiple scan. We saw a really strong relationship between those two data sets. And so we recommend making quick and efficient measurements with a single scan in the field. Of course, several different important variables impact the accuracy in that data. Of course, as I just showed, species composition impacts leaf mass per area. Of course, height above ground and the distance from the sensor also introduces some negative bias in our estimates. And then occlusion, of course, is a very important variable for us to be considering when we make those decisions. And then I just wanted to end with a couple of quick examples of what this data looks like pre-prescribed burn treatment and what it looks like post-treatment. So here I show a vertical profile of the canopy bulk density pre-treatment. Specifically, I want you to focus in on the surface fuel strata below 1 meters or so along the x-axis here. If I go to the post-treatment data, you see that the surface fuel bulk density has been really reduced. And also you see that the maximum canopy bulk density has changed a lot. So just for fun, I will flicker back and forth a couple of times. And so you can see at what height canopy bulk density has been most impacted. One important thing is that the base of the fuel canopy has been lifted, as I show here with this yellow bar. So that's one other thing I wanted to point out. Here, from a low burn severity prescribed fire, I show another example. Once again, this fire also, when you look at the pre-burn and post-burn data, it largely changed the surface fuel structure below 2.5 meters or so, whereas the rest of the canopy bulk density remains more or less the same. So in conclusion, just to quickly summarize, we think that LiDAR data can be a really robust and efficient way to measure fuel structure. And then once again, single scan TLS can accurately measure this, which surprised me, but I'm happy to report that it works well. Once again, here's the publication that I've referred to. And so if you wanted to revisit any of the details, you can look up this paper. In addition, I wanted to say that Jonathan developed his processing code in Python, and he then published his code on GitHub. And so you can look him up if you want to implement his code. Essentially, this workflow will take you from your terrestrial LiDAR scanner and give you the vertical profile of the leaf area density measurements. In addition, he tried to generate and output some additional variables that could be used with fire behavior models. You could check those out if you wanted to. And then finally, I just wanted to share Jonathan's email address and my email address if you had any follow-up questions about the specific details of the study. With that, I will stop talking and take a couple minutes to answer questions if there are any. Maybe I will stop sharing my screen for a second.
Guess I was muted there. Thank you so much, Dr. Sankey. We do have time for questions. So again, if you have questions, if you would type them into the chat box, and then we'll get Dr. Sankey's answers. And actually, we're not that many folks. So if you do have a question, feel free to raise your hand and I'll unmute you. Diana, I'm trying to unmute you, but I think you might be able to unmute yourself.
Yes, thank you. Thank you, Techie, for your presentation. That was really great. And we very much appreciate that the code is available. And, to your message at the end, that's super helpful in disseminating and making the opportunity available. I just had a quick question about cost savings. Ultimately, have you looked at, remember at the beginning or early in the presentation, you were saying the traditional methods for acquiring this data, is this pathway, and this is a way that we may be able to expedite getting that really important data. Have you all looked at what the potential cost savings could be for groups seeking to, utilize a method like this?
Yeah, so I haven't sat down and calculated the cost associated with labor, but I will just quickly say that, if you wanted to have like a conventional measurement in the same size plots, we were using a 3-person crew. Whereas if you were to do LiDAR measurements, you would only need 1 person, in particular from a single scan. And also, we estimated that the LiDAR scan itself would take roughly about 20-30% of the time that you would need per person to make the full detailed measurements by hand. And so those are kind of the rough estimates that I can provide. And so you can kind of think about the labor costs associated with that.
Thank you, that's very helpful.
Any other additional questions? Not seeing. Oh, go. Edwin, go ahead. Or Edward, sorry. You should be unmuted. Maybe not.
There we are. Hi, thank you for the presentation. Just another thought I had in sort of this, I guess you'd say practical implementation side. Have you coordinated with any kind of controlled burns, fire practitioners who are working in the field and um, finding out if they have changed any methods or ways of implementing a prescribed fire as a result of the data that you've given to those groups?
Mm. Yeah, really interesting question. Um, we're here in Flagstaff, immediately or within the Coconino National Forest, who have actually been implementing prescribed burns around here. And we have gone out with them to several prescribed burn areas before and after the fire. And then we showed them the data afterwards. One thing that they noticed was that, of course, across the burned area, the fire is burning at varying burn severities and intensities. And so they were, I'll say, two reactions they had. One was they were pleased to see actual quantifiable impact of the prescribed burns around our forests here. Secondly, they were surprised by how variable the fire impacts were. Beyond that, they weren't like, oh, I'd love to do this myself or do the LiDAR imaging myself or anything like that. But they were pleased to see that we can actually quantify their prescription management efforts and monitor the effectiveness. So, and they were pleased to see that we could actually move the scanner around and cover a fairly big area relatively quickly. So, so yeah, those were the reactions we've gotten so far.
Yeah, thank you. It's an interesting technology, and I can say in our particular park unit, we have forested areas where understory, particularly blueberry patches, are a primary resource, an ethnographic resource that's important to people in the area here. So I could definitely see how this kind of technology could be used to kind of identify and monitor those understory patches for more accurate management of those areas we know have that type of vegetation. So it's interesting to think about.
Yeah, for sure. And what you said just reminded me of like some folks don't necessarily want to see a whole bunch of prescribed burns happening because of smoke and etc. And for land managers who are doing those treatments, it is nice to be able to quantify what they burned and how much they burned and what resources they're preserving, etc., with like a visual data set like this. And so I think that is another nice aspect of this kind of data, just because it's so visual.
Any other questions? Well, please join me one final time for thanking Dr. Sankey for joining us today. Remember, we have one final seminar coming up April 23rd. That's Mallory Davies representing the Desert Southwest CESU. And that talk is about the long-nosed bat research. A decades-long research in the Desert Southwest. So we hope you'll join us for that. Again,